We hit rock bottom in the last lecture. And now, having gone sort of from over here where we were talking about how to program computers all the way down to sort of the physics of molecules at the very bottom, we're now going to pick up where we left off, and we're going to talk about how to make computers work faster. Okay, so this is kind of a little graph of how the course goes versus time, where this level over here sort of represents how deeply we're looking inside the various parts. So now we're kind of going to jump back to where we were at the beginning of the course, and we're going to talk about sort of higher level things in terms of building the architecture of these machines, and in particular for improving performance. So today's lecture, and I see that you guys learned a little bit about it in recitation in the last section. It must have been the recitation teacher was bored or something like that, is going to be this thing called pipelining. And this example is used both in the Hennessy and Patterson book, and also I think I used it first, so that's probably how it got into the Hennessy and Patterson book. But, you know, while all of you guys, I'm sure, are well past this stage in your life, well, maybe not. Oh, yeah, just give it to mom, right? There's this common chore in college life which involves doing the laundry. And in general, you need a washer, you need a dryer. And I always ask the students how long the washers take, and they usually tell me it takes around 20 minutes, which is the propagation delay of the washer. And typically, the propagation delay of the dryer is around 40 minutes. And of course, the trouble is that at MIT, half of the dryers are broken, right? And so the dryers kind of take forever because they don't get warm. But let's just assume that those are what the numbers are for doing the wash and doing drying it off. Now, oops, there we go. And so obviously, if you do one load of laundry, how long does it take? The answer is, I hope, 60 minutes total. The setup time and the hold time and the propagation time. And is it a contamination time if the laundry's dirty, or is it a propagation time if the laundry's clean? Oh, then the people that left theirs before that you have to take out and throw on the floor, right, before you put yours in. Assuming all of those times are negligible, the time to do the laundry in total is 60 minutes, or 1 hour. And in general, when you have a combinational logic circuit, and you have two elements that have a propagation delay TPD1, and in this case I'm talking about the maximum propagation delay of the circuit, and you have another element that has time delay TPD2, and these operations have to happen in series with each other, like doing the wash and doing the dry, then the total propagation delay of the circuit is TPD1 plus TPD2, just like you would expect. Okay? So that's fine. There's another question that we might ask, which is, if this is how long it takes to do one load, how many loads per minute, since we're operating in minutes here, can we do? And that quantity is called the throughput. Sort of a rate. At what rate can we put new pieces of laundry into the system? Now, if we're being very naive, we'll get one answer, and if we're being more sophisticated, as I'm sure all of you are, we'll get a different answer. So let's say that we're being naive. Do it the Harvard method. How many people here went to Harvard? Good. Uh-oh. So usually, there's usually some guest student at MIT also, so we make fun of them too. But, you know, if you go to Harvard, where you have lots of free time, you know, because they don't really work that hard up there, you know. What they do is that, of course, they do the wash, then they dry that wash, and then they put the next load in, and then they dry that load. And so the throughput in general is going to be 1 over the latency. And let me introduce that term too. That latency is a question of how long does it take for a single item to go all the way through. It's really a propagation time. Okay? Whereas throughput, if you're being naive, is 1 over the latency. In other words, you wait for one item to go all the way through before you feed in the next one. Okay. But I'm sure all of you can see where this is heading, in that if we do it the MIT method, of course, or actually I guess I should say the Ars Digita method, then we can make use of some amount of parallelism and keep both the washer and the dryer busy, at least for part of the cycle, at the same time. Now, the latency, the time that it takes for a single load to go through, does not seem to have changed, although it certainly is the case that we can save on the amount of time by having 2 units go in at the same time. And so if you think about it, it's going to be 20 minutes to get the first thing through the wash, and then it's going to be 40 minutes. So this is going to be wash 1 and dry 1. But while dry 1 is going on, wash 2 can be going on. And then we're going to have to wait a while until we can do dry 2. And then we're going to be done. So the total amount of time that it's going to take doing it the smart way, rather than being twice the propagation delay of the whole circuit, which would be 120 minutes, is going to be 20 plus 40 plus another 40, which is 80 plus 20 equals 100 minutes. So we have saved 20 minutes off the time to do this whole thing. And you can imagine that if we were feeding more and more laundry into the system, where is the bottleneck? Is it the washer or the dryer? It's obviously the dryer. And it's clear that the washer, even though it will get done in parallel with the dryer over here, and it'll get done early, so this is only 20 minutes, half of the time here, for half of the cycle the washer will have to sit doing nothing. And in fact, we're free to either start the load here and wash it at the beginning of the cycle, or to start it over here and wash it towards the end of the time, but everything gets in sync. Now, in the pipelined system, and this is the word that we're going to use for a system where several things are running in parallel down the line, as if there's a big pipe and there's a lot of stuff going down the pipe, some in earlier stages of the pipe and some in later stages of the pipe. What determines the throughput? So here we have TPD1 and TPD2. So this one over here, these are the answers if it's non-pipelined. What if it's pipelined? What is the latency of the circuit going to be? Well, that's a hard question to answer. It's a hard question to answer because the latency of this load of laundry, of wash 1, laundry number 1 came into the system here, took 60 minutes to get done, and came out. And that latency is the same as what we had before, 60 minutes. But the latency of this guy over here, this guy came in over here and took 40 minutes to get done, and another 40 minutes. So there the latency actually went up because it had to wait around until the dryer was free before it could move on. So that's kind of hard to answer. So let's put that off for just a second. And let's ask ourselves perhaps the easier question, what's the throughput? And this is going to be in the pipelined case. And what's the answer going to be? How often can we either insert clothes into the system, on average in steady state, or how often does clothes come out of the system, on average in steady state? Now, hopefully those numbers are the same, because otherwise the machine is eating the clothes, right? Or it's creating clothes out of thin air. But what is the throughput? How many batches of laundry per minute goes through here? 1 every 40, right? So it's actually, if we have a combination like this, it's 1 over the max of TPD1 and comma, let me get this right here, TPD2. And this is an improvement over 1 over the sum of TPD1 and TPD2, which we had before. Because we just look for where the slowest element is, and that's the one that sets the maximum rate at which things can go through.
So do we neglect our initialization time with throughput?
Yes.
20 minutes?
In general, when we're measuring throughput and latency, the question is, in steady state, if we're just operating a laundry business, how fast do the things go through? How about the latency? What's that going to be? Now again, let's think about this in steady state. So there's this transient at the beginning. The first load only takes 60 minutes to get done. But thereafter, as soon as we put a load in, how long does it have to wait? 40 plus another 40. So in this case, it's if there are n stages, so n here, I'll put down number of stages times the max of TPD1, TPD2. And since the number of stages in this case is 2, it's just going to be 2 times the max of TPD1 and TPD2. That number may be more than the simple sum of these two. It's taking the greater of these two and doubling it, as opposed to just taking the sum of all of them. Now, if it's the case that each of these has the same propagation delay, then the number of stages times the max of whichever one it is will be the same as just adding them all up. But if these have different propagation times, then pipelining the circuit will actually make the latency slower. It'll take longer for it to go through. Because what a pipeline is what's called a synchronizing delay, just like you learned about in the case of the finite state machine, where a register was used to delay and synchronize the transfer of data going around and around the loop. And so what's going on here is that we're saying, even though the wash gets done here, we're going to delay it and have it sit in the washer until the clock goes off, which we're going to put here. In fact, one can think about a system like this as being clocked every 40 minutes. Every 40 minutes, the timer goes off, bing, and we transfer everything over by one click. 40 more minutes go by, and we transfer it over again by one click. And so pipelining can improve the throughput, but it may make the latency worse. Okay. Now let's talk.
Latency.
Yeah.
Why are we measuring the left-hand endpoint as far over as that?
Excellent question. We have to think of this not only in terms of a circuit that has 2 elements, which I've drawn here, which is the simplest, but let's say it had 3. TPD3. Okay, so we have the washer, the dryer, and the fluffer. Okay, kind of fluff the clothes up, I don't know, or press them, or no, okay, the folder, ah, yes, there's the folder. Good. The folder takes longer than any of those. Okay, and the folder. As this chain gets longer and longer, there's no possibility of delaying before we insert something into the thing. So let's take a look at this. Let's say that wash was 20 minutes, dry was 40 minutes, and folding, I don't know, you want to make up a number? Okay, so a single load of laundry goes in and gets washed, okay? Now, we have to think of this, here's the next time it gets dried. So this is 40, this is 20, and then it's going to try to get fluffed in 60. Okay. The next load of laundry goes in, and it's going to want to use this fluffer, or excuse me, this folder during this time here. So that's going to take 60. And then the next one's going to go in, and it's going to want to use the folder over here. Okay, and so forth and so forth and so forth. That means that preceding this, we have to use the dryer. Well, somewhere in here, and we're not sure where, there's going to be 40 minutes of drying. Okay, and somewhere preceding that is going to be 20 minutes of wash. Okay, but we don't know quite where. Well, if this is 40 minutes of drying, then somewhere in here has to be 40 minutes of drying. And somewhere, I think this example is not going to work. I'm going to change things a little bit. We're going to make this 10 minutes of folding. Okay, this is not to scale, obviously. Okay. Okay. So somewhere in front of this is 40 minutes of drying. Okay? Now, how can we fit things in so it makes sense. Well, the only thing we could possibly do is have this edge butt up against this one here, because we can't use the dryer at the same time. And then, kind of making this a little bit more to scale, we now have freedom where to put the folder, but let's just put it there. And that's without loss of generality. And then the wash is free to happen, 20 minutes of wash here. Okay, now there's going to be 40 minutes of drying in here, but this 10 now is going to take up a part of that, and so that goes up to here, and now there's going to be 20 minutes of wash here. And so what you notice is that it sort of doesn't matter when. This example doesn't work either. Okay, after we fold it, we're going to put it away, and that's going to take 30 minutes, okay? P. I have to make this work. Okay, got it. Folding, and now putting away, which takes 30, we are basically forced to wait. We have no choice in this folding here but to idle ourselves. And for that reason, the latency is determined by the clock period that we run the thing at, not by whether this thing is on the left or on the right. Okay? So if you want a better answer to that, so it'll take me a long time to do this here, but do an example where you keep changing the times and there's several stages, and what you'll find is that except in these special cases where there are only two stages like the washer and the dryer there, in general the rule is going to be we find the element with the longest time and we just say that the latency is that time times the number of stages that are in the plant. Okay. We can go through it more a little bit afterwards, but
Number of stages divided by 2, is that what you remember?
no. This is equal to 2. The number of stages is equal to 2 in this case, times the max of the two things. Okay. So the latency is a measure of how long it takes a single item to pass through the entire system. Okay, and I've written the answers to this slide up on the board here. And the throughput is the rate at which the objects go through the system. And what pipelining allows you to do is it allows you to drastically improve the throughput of the system. What it does not allow you to do is to improve the latency of the system. It is impossible to improve the latency of the system because the item that's going through still needs all the operations done to it. And those have to happen in series, one after the other. Like a car going through a car factory still needs to be assembled and painted and tested and all the different things. And that each one of those things takes time. And at best, by using an assembly line of many people working on the car, as opposed to one guy who will do one car in sequence from the beginning to the end, the latency can only get worse. Why would the latency get worse? Because when the car goes from an operation that is fast to an operation that is slow, it'll have to sit around waiting for the slow one in front of it to get done with that stage before it can go. So the latency will tend to get worse. Okay? How long it takes one data item to be processed all the way through.
Although, if we were doing laundry and the slowest thing was to dry, we might get 2 dryers so we could wash.
That's
and
absolutely
double up
right.
on the slow.
Right. So there are other ways that you can optimize the system by creating pipeline stages that effectively have the same time delay in them or that somehow have the same throughput so that you can balance the pipeline well. And we'll talk about how to do that. That's absolutely right. So for instance, you might want 2 dryers as opposed to 1. Yeah.
Even with putting away the laundry, I wouldn't visit each bedroom and open each dresser drawer. I would instead bundle all my clean laundry and do all the putting away at once. Is that consistent with the pipelining? This is one case where if I bundled everything together,
Right.
it'd be easier to.
Well, I think the analogy breaks down because you're thinking about only one person being involved. And in a pipeline thing, you have to think about everything in the chain has an operator. And so there's this person free to do nothing else but put away the clothes.
I'm thinking
And
about
so-
memory, where it would be reasonable to access.
Oh, to store up a whole block and
kilobyte
something and then,
consecutively because it's likely
Sure.
you're going to read
Sure. So there are. That's actually it's called blocking, and it's slightly different than the pipelining things we're talking about here. Okay. So now let's switch over from the laundry domain into the computational domain. This is very close to what you saw before in recitation. If I had a circuit that's trying to do a operation sort of like this tree here, and we're trying to add 4 numbers, A, B, C, and D, and we are using 3 adders to do it. So here's A and B, and here is C and D, and here's one adder, and here's another one, and then we add the 2 sums together, and we come up with the answer. If each one of these has a time delay of 1, then without pipelining this circuit, if I were to ask you what is the latency of this circuit, how would you figure it out? Well, we actually haven't talked about that yet, but you know from that thing that if this has a propagation delay of 1 and this has a propagation delay of 1, then the sum of the propagation delays determines what the propagation delay of the whole thing is. But what you haven't talked about yet is how do you figure it out if there's several paths to get down to the bottom? And the answer is that you think about it and you say, oh, I know what the answer is. It's the maximum. If I present all this data at the same time, it's the maximum propagation delay along any path from the beginning to the end. So, for example, if there was a third adder in here that was adding B2 in, and this had a 1, then the latency of the whole circuit would be what? 3, even though there was a sneak path here, which was 2. Let me ask a real quick question. If the contamination delay of each of these things was 1, what would the contamination delay of this circuit be? 2. Good, because it's the minimum of the propagation times, or of the contamination times. Because once you put trash on here, it's the fastest the trash can get through, which is this path here. Once you put good data on there, it's the slowest it takes to get there, which in this case is 1. So let's stick to the example that's on the board there, or on the slide, which is this one here. How can we make a circuit like this operate more quickly than if we just hooked up the adders just like this? And the answer is that we could put registers in over here, and in general, we put one on the output as well. Like so. Okay? All right. Don't know if that's on the next slide or not. Okay, we figured out what the latency was and the throughput. But adding the pipeline in, what we find is that we can clock this circuit how often? Well, let's say that there was a clock here that was connected to all of the inputs. So this clock went off simultaneously. Okay? So every time this clock goes off, all 3 of the registers take a snapshot of the input and propagate it to the output. Now, right now, we are going to ignore and say that it is negligible the propagation delay of the register itself. So the TPD, clock to Q, of the register, we're going to assume to be so small we don't even need to think about it. All of the slow stuff happens in these adders here. So how often can I clock this circuit? Well, period of 1, right? Every time I clock this, let's say it takes very little time for the Q to come out here. The propagation delay to get to D here, oh, and I'm also going to say the setup time is very small. Okay? I can clock this thing 1 unit of time after I clock this one here, which is to say that I can put in a clock over here which has a period of 1 unit of time. Like that. In this case, it's 1 TPD of an individual unit, which in this case I've said to be 1. And furthermore, if I present the data here, if this data itself is coming from a bunch of registers, which I assume it is, I assume that the circuit that precedes this is pipelined as well. In other words, it ends with a register. And I know that these are all being clocked by the same clock as this thing here. Then that's going to work also. Okay? But what isn't going to be true is that the latency is going to get any better. It still will take a latency of 1, 2 units of time in order to get a set of data values from here to the end. Okay? In this case, the pipeline is perfectly balanced. And so what that means is that the time delay in this stage of 1 is the same as the time delay in this stage of 1. And so the latency doesn't get worse. Okay, because 2 times the maximum of the time delay between the stages is 2, right? And that's the same as what the latency was before we pipeline the thing. There's no idling around in this circuit over here. But the throughput does get a lot better, right? The throughput here is 1 data item every time unit instead of 1 data item every 2 time units. So we've made that better. And it means that the calculation, the final calculation over here, will be done simultaneous with the preliminary calculation for the next piece of data here. Just as if this was an assembly line for cars and the finishing was being done here while the painting was being done here to the next car in line. Okay. So if we have many data items to process, a pipeline circuit like this can drastically improve the throughput. And we assume in general when we're doing a circuit like this in class that the propagation and contamination delays of the registers are 0 as well. Of course, when you design a real circuit like this, you have to add the propagation delay of the registers to the propagation delay of the logic that's in between the registers. Plus, you have to add the setup time of the register before you can let the clock go off again to the next one. Now, in general, we're going to use a straight line like this as opposed to drawing the whole register in order to fill in order to show that there is a register in that path of the circuit. That just makes it a little bit easier to do. Okay, let's take a look at this one here. We have 2 multipliers, and they take time units. They take 2 time units to get their job done. And then we have an adder at the end that takes 1 time unit to get through. In a circuit just like this without pipelining, the latency is going to be the longest path from input to output, which is 3. And the throughput is just 1 over the latency, right? But if we pipeline it, the throughput can get better, and the latency will get worse. And the way we'll pipeline it is we'll put these registers in here just like the other case. But now the question is, how often can we hit that clock? What is the period of the clock that we can use to sequence data through the system? And that is determined by the maximum propagation delay between stages. The assumption, again, is that there is a circuit like this one that ends in a register that's feeding this one here. And so the time between that register, which is up here, which is off the same clock as this one here, what's the clock period going to be? 1 cycle every 2 time units. Okay? So the throughput is 1 over 2, 1 data item every 2 time units. And the latency is the number of stages, which in this case is 2, times 1 over the throughput, which in this case gives you 4. And remember, before the latency was 3, and now the latency is 4. And why is that? It's because even though it only takes 2 time units to go through here, and only 1 time unit to go through here, the result will be sitting at the D input of this register waiting for the clock to go off. And the clock will go off 1 time unit later. Okay, and that may seem silly over here, but this in turn may be followed by another item, which itself will take a longer length of time to do. Yeah?
When would we be concerned with latency? Because it seems as though in most situations we'd be doing such a volume of calculations that throughput would be our overriding consideration. We wouldn't really bother so much about having bigger latency. So
in general, that's true. But let me give you an example. Latency is very important in feedback systems and in some communication systems as well. So if you're having a telephone conversation and you're going through a type of speech processor that has a lot of work to do in order to compress your speech into very few bits, in general, you pipeline those things, and the throughput is very, very high. But you need to be concerned about the latency, because if the time delay on a phone call gets too long, people don't like it, okay? So that's a typical case. If there's a feedback thing, that would work in the same way. You can't tolerate a latency that is too slow. Okay, how about this one over here? how do we do this? Well, here we have differences within a pipeline stage, and also each one of these is a little different. So what's the minimum clock period that I can use if all of the dashed lines have registers in them and they're all clocked at the same time? It's going to be 4, right? It's whatever the slowest element is within a pipeline stage. And how many stages are there? 3. So the pipeline throughput is 1 every 4 time units, and the latency is 3 times 4, which is 12. Unpipelined, the circuit is a lot better in terms of latency, because the longest path through it is 4 plus 1 plus 1, which is 6. Notice that's half the latency we had here. But the throughput is worse. It's 1 every 6 time clicks as opposed to 1 every 4. Okay, now, this gets to the blocking question. What if I gather all my laundry together all at once and put it away all at once? The way MIT students actually do laundry, and I'm sure none of you do it this way, is that they wait for a long, long time. And they gather together 8 or more things of laundry, and they go downstairs in the middle of the night to the bottom of the dorm, the basement of the dorm, and they take over all of the laundry machines there at the same time. And actually, if you go to the bottom of the dormitories there, you discover that there are, just like you guys said, twice as many dryers as there are washers. And so, in fact, you can achieve a steady-state throughput using a system like this of what? 1 basket or 1 clock cycle every 20 minutes, because you can keep alternating back and forth between the dryers, right? And the throughput in this case, since you're using 4 of them at the same time, is not 1 every 20 minutes, but 4 every 20 minutes. So you can improve throughput not only by pipelining, but also by parallelism as well, which is the idea of having 2 sets of these, and furthermore having 4 of them in a row that you feed 4 into at the same time. So you see here 2 kinds of parallelism. One is 4 simultaneous being used at the same time, expanding the amount of hardware by a factor of 4 and clocking all those in at the same time. And the other is called round-robin parallelism, where we expand the amount of hardware by 2, and we alternate back and forth between these 2. So in this case, it's 4 every 20 minutes, but the latency is still what? 60 minutes, okay? And in this case, the fact that these are out of phase by 20 minutes means that the latency actually is 60 minutes. So that doesn't change. So interleaving is what that kind of round-robin method is called. And so in particular, instead of feeding 4 data items simultaneously into the washers here, what we could do is, since these take 20 minutes each, every 5 minutes, we could have a multiplexer, or excuse me, a demultiplexer over here, shuttling the laundry into a different washer every single time, every 5 minutes. And every 5 minutes, we take out the laundry right before we put one in. And so we just keep going around and around and around and around. And so we've effectively built a device that has 4 times the throughput of a single washer, but the latency is still 20 minutes. Okay? You cannot change the fundamental issue that it takes 20 minutes for the single load of laundry to get done. It's the old joke, right? Getting 9 women pregnant does not have a baby in 1 month, right? That doesn't work, right? So, but the joke is basically a latency and throughput joke about pipelining, okay? Okay. The way that you would interleave a circuit to actually do this with registers and selectors and things like that would be that either you control the clocks to clock it out 1, 2, 3, 4, 1, 2, 3, 4, going around like this, or the clock could run at 4 times the rate, and you could have an enable on each one of these, and you could choose which one is enabled for the data to get through. And that would be a way of interleaving when the data is sampled by these different registers up here. The units would be over here, and then the selector would be told to sweep around and around and around, picking up the data. And then the unit as a whole would have a throughput that was 4 times as high as the individual unit here and a latency that was just the same. Okay, when you make a pipeline, it's extremely important that you're careful that the pipeline is what's called well-formed. And what that means is that there are the same number of registers along every single path from any input to every combinational unit. Okay? And so let me see if I can explain why that's true. Let's draw a tree that has more adders in it. Except that's a full binary tree. So let's kind of make it a little different. And let's say that we're in fact not going to add up 4 numbers, we're going to add up 5 numbers. We're going to do it like this. A, B, C, D, E. And now I have time unit of 1 in each one of these things. And now I want to pipeline it. Okay? So I say, okay, let's do it. We're going to put a register on the output because that's kind of the conventional thing to do so that when we feed the next stage, we'll have a register. And we'll put one over here, and we'll put one in each of these places, and then we're done. You think this thing's a pipeline that's going to work? We simultaneously feed A through E to here, and we hit the clock. What happens? E goes directly to here and combines with a result that is 2 clock cycles old. In other words, E races ahead of the data values A through D and gets out of sync with them so that, in fact, when we finally do get A through D added up down here, we're going to be adding those to E that's 2 clock cycles ahead of these. And that's bad. Okay? So what we want to do is we want to ensure that there are the same number of registers between all the inputs, whichever ones are used, and every input to any part of the circuit here. And it turns out that you can do that, you can ensure that that's true if the number of registers, and this is kind of a neat proof for you guys to do on your own, if the number of registers between any input and the output are the same. Well, let's see if that's true here. Here we have 1, 2. 1, 2, 1, 2, 1, 2, and then we have, I'm sorry, 3. 1, 2, 3. Here's the output. And here we have just 1. So that's wrong. So what do we need to do here on this wire? We need to insert 2 extra registers to time delay E so that these other data values can catch up with E, and so it can be considered at the same time. And this is called a well-formed pipeline, and it's extremely important to not mess this up when you're designing pipelined circuits. Another way to think about it, it's possible to custom order your car, right? At least in the US. And you can say, well, I want a purple car, and I want air conditioning and power steering and this and that, right? Well, different parts of the factory are building the different parts of the car in parallel with each other. You sure hope that when they finally come together in a car, that your order is in sync in terms of all of its different parts, that the steering part is going to be the steering that you wanted, and that the radio is the radio that you wanted, and the color is the color that you wanted, even though the time delays for those things to get to a common place where they get put together in the car may be different. Some parts may have to be delayed so that the car that gets put together is the one that's associated with all the right same things in sync with each other. Because otherwise you're going to get the power steering that the other guy wanted in your car rather than the one that you wanted. Okay. There are several ways to do it, but the easiest way to do it is when you're drawing a pipeline stage, draw it across the entire circuit. First of all, make sure the circuit goes from in to out in a straight line, no looping back or anything like that. And when you draw a pipeline stage, cross all of the wires. And so this pipeline stage crosses all of the wires here. This pipeline stage crosses all of the wires here. And thus, I guarantee that the number of stages between any input and the output are the same. And that's true everywhere in the circuit. even if I'm here looking up, the number of stages going up is going to be the same. And so this circuit here is well formed. It means putting registers in places that they seem to be doing no job at all, other than to delay the signal and to hold on to the several values of E as we get ready to synchronize them and add them up to the values of A through D on the way down. Alrighty, so that's the business of making it well formed. So-
I'm lost by the diagram. Why can't E feed into the second level? Won't that shorten this process?
Oh, why can't E feed into there?
Yeah.
Well, okay, we could do that too.
So won't that shorten the process by one?
Well, not really. So we put it in there. That means we need one less register here, but it still takes just as long for the values to get through. Now, unfortunately, this is a 3-input adder. The previous circuit was only two input adders. So if we were constrained to do that, but you see how we would change the number of pipeline stages in E if we did feed it into this level. It would go down by 1. Okay, or we could feed it into here, in which case it wouldn't need to go down, wouldn't need to be registered at all. It could just go straight in. Okay, good. In general, the way that you can guarantee that this is true is what we call adding the registers to the output, and then you sort of migrate them up, just as I've done here, to earlier stages in the pipeline. If you want the pipeline to perform as well as possible, what you do is if this element here takes, now let's try this in a slightly more fancy way here. Let's say that this element here took 2 units of time for some reason that we don't know. Okay, maybe because the numbers, by the time you add them up, get real big. So this unit here takes 2 units of time. Let me ask a question. Is it necessary to actually have 3 stages here? Or am I sort of wasting pipeline registers? I only need 2 really, right? So I want to surround the element that's the bottleneck, that's the slowest one, with pipeline registers. And then over here, I can then go around the circuit and say, I can accumulate up to 2 units of delay here and not use a pipeline register, and I'll still get the same performance out of the system. Right? And remember, of course, that there's a register on the output of the stage that feeds this thing here. So again, the technique is look for the element that is the slowest, surround it with registers, and then go through the circuit and kind of break up the circuit into sections that have that latency or less. Think about the example of the car. If there's one part of the process of building a car that takes a long time, that becomes the slowest unit in the assembly line, okay? Let's say it's putting the transmission to the engine. Let's say that takes a minute. You put that in. And let's say that right before you do that, you put in a bunch of bolts and you put in the weather stripping on the door. And each of those takes 5 seconds. You know, should you use one person to do those things or 2? So it takes one person, okay, putting the transmission, okay, which looks like this, to the engine, which looks like that, okay? That's one person. And how long did I say it takes? 1 minute, okay? Then previous to that, he's a real strong guy, right? So that's, we're going to surround that. We're going to say that is a pipeline stage. Previous to that, there's screwing in a few bolts, okay? Okay, like that. And there's also putting the weather stripping on the door, okay? And this takes 2 seconds, and this takes 2 seconds. Well, let's make it realistic. This takes 30 seconds, and this takes 30 seconds. How many people should I use to do these 2 jobs? Should I give one person this job and another person this job? In other words, should there be a work cell here that then gets handed off to this one, that then gets handed off to this one? And remember, all the work cells have to get clocked at the same time. Bing, chunk, the whole line does a transfer. That would be a waste of manpower, right? We just have one guy that does both in series without pipelining, puts the weather stripping in, and then puts the bolts in, and we make that be the work cell, because that is 1 minute or less. Okay? And in each one of these things, we try to add up as many things as we can, and we chunk the job according to whatever the latency was of the longest part of the pipeline. And that'll give us the best performance without using an excessive number of people to do the work. In the same way, if we don't want to use an excessive number of registers to form a pipeline here, we look for the element that takes the longest time, surround it with registers, and then chunk the rest of it so that the propagation between chunks is that number or less, but as large as possible. Make sense? Yeah.
Can I just go over that
Sure.
example that you read about? You don't have a problem with E being added to old A, B, C, and D data because you have the one register before the last adder, but have you changed the clock cycle or something?
In this case, the clock is going off once every 2 time units. So now this time is now 2.
And that's because what?
And that's because this element I changed to be 2 time units long. So we have to wait 2 time units between when we clock this and when we clock that. And thus, we give 2 time units between when the data is presented here and when we clock it out here. Now, E arrives, right away to here. A through D take 2 time units to go through this stuff, but they all wait for 2 until this thing clocks off.
And that has to be balanced like that.
And that has to be balanced, right? Yeah. Good? Okay.
Suppose the levels are 2, 1, 2, and 1. You're suggesting that we chunk them together as 2.
Well, 2, 1, 2, and 1 is very hard. Okay? So let's make it simple. Okay, there's a unit X, okay? And there's 4 X's. And it's 2, 1, 2, and 1. That's really rough, okay? Because first of all, we need a register on the output. Then we surround the registers, the ones that have the longest time, with registers. And we're going to assume there's one up here, okay? Well, there's nothing left to do.
We have 8 here.
We have 1, 2, 3, 4 time units,
Right.
a total latency of 8. Yeah. And this is sort of a worst case, okay?
But if we chunk them together as 3 and 3, we'd have 6.
But then the throughput would not be as high. The throughput here is 1 every 2 time steps, as opposed to 1 every 3 time steps. So it's a question of what you want to minimize. Do you want to minimize the number of registers, or do you want to increase the throughput as much as possible? So it's a trade-off there. Okay, let's look at this example here. Very similar to the one I had on the board before, okay? Here we have the multiplier that takes 2 time units, so we put registers around that one. Okay, remember, we're always going to have a register on the output. And then looking backwards, we chunk it so that the other sections have the latency as large as possible, but less than or equal to the latency of the longest element, which in this case, we just do it at 2 over here. And notice, of course, the way that we draw this across all the data paths, which are going from left to right, and thus we ensure equal delay through every data path to every element in the circuit. Okay, there's never going to be a skewing of one piece of data with respect to the other one, if we do it in this case. All righty. A couple questions before we talk about how pipelining is actually used within the beta. Okay, assuming a circuit is pipelined, this is like what you might see on a quiz, for instance, on Sunday. Actually not. This is not going to be on the quiz on Sunday. The quiz on Sunday, I should tell you, is going to cover through yesterday's lecture. Okay. This is all for next week. Assuming a circuit is pipelined for optimum throughput with 0 delay registers, in other words, the setup, the hold times, the combination times, and the propagation times are assumed to be negligible. Is the pipeline throughput always greater than or equal to the combinational throughput? The answer is yes. Who wants to say why? Why is the pipeline throughput always greater than or equal to the combinational throughput? And combinational means it's just the logic with no registers at all.
Because if the registers have 0 delay, then we're never changing what any particular piece of data is doing.
That sort of sounds like a latency argument.
Well,
This is a throughput question.
right, but we're never making it harder for data to get in at the top.
I don't buy your answer.
Oh,
Sorry.
we're never leaving.
That sort of sounds like a Harvard answer, doesn't it?
We're never leaving something in the way for longer than we would in a non-pipeline circuit.
Still a
It's
latency argument.
preventing us from putting more data in at the front.
still kind of a latency argument. What is the throughput of a non-pipeline circuit? 1 over the sum of all the latencies. Okay. What is the throughput of a pipeline circuit?
Whatever the maximum.
Okay, can the sum of a bunch of numbers ever be less, excuse me, than the maximum of one of the numbers?
No.
That's the answer. Okay. Good. Knew you had it in you. Better dead than crimson, right? Isn't that how it goes? Have you ever seen those shirts? No? No. They sell them at MIT. So. This is all just a joke. Don't take it seriously. Warfare, yes. Is the pipeline latency ever less than the combinational latency? No. Why is that? That's actually what you answered, which is?
That we're not routing around any pieces of combinational logic that we need to do.
Good.
To do an answer.
Absolutely right. Okay. When is the pipeline latency equal to the combinational latency? And here the answer is just down here. If the contents of all the pipeline stages have equal combinational latency. In other words, if our chunking happens to fall exactly on the latency boundaries. In that case, the data arrives at the D input of the registers for the pipelining just before the clock goes off. In general, what we care about when we sell a processor, what the customers will pay top dollar for, is how many MIPS the processor are, where a MIP is a million instructions per second. Okay, and these days, the answer of MIPS is somewhere around 1,500 or a few thousand MIPS. And what this is a measure of how many instructions per second the processor can execute. And so it's a question of what the frequency is of the clock in terms of cycles per second, plus how many cycles per instruction there are, and you divide one by the other, and you get instructions per second. Now, if we want to make this number as big as possible because we want to sell as many processors as we can, what can we do? Well, we can make the top number bigger, we can make the bottom number smaller. And so if we want to lower the number of cycles, of clock cycles per instruction, the first thing that we can do is we can make the instructions very simple. And that means that the computer can execute one of them every clock cycle. And in general, these reduced instruction set computers, or RISC computers, like the Beta that we've built here, can execute one instruction. It only takes one clock cycle to execute an instruction. Turns out that there are, well, this should be a 1. I'm looking at this, what the heck did I mean? Less than 0. You cannot take negative clocks to execute, except on Star Trek, right? And everything's kind of weird. But in general, you can lower the number of clocks per instruction. And we're going to talk about that actually in a lecture next week, where we talk about computers where they actually are doing several instructions in parallel at the same time. The other possibility is to increase the frequency of the clock. And the frequency of the clock, if you remember the diagram of the Beta before, is limited by that percolation time. How long did it take the data to percolate all the way down until we could clock the registers that were down at the bottom, in which case the data began again at the top to percolate down. So if we can cut the percolation time down, then we can increase the frequency along this longest combinational path inside of the machine. An alternate way, yes?
About how many clocks per instruction are there for the Intel machines?
The latest ones are actually 1, but the early ones were, I don't know, 10 or something, anywhere between 5 and 10. So
For like 486?
I don't know about 486, but 286 was pretty darn slow. And so those machines were CISC machines, and they used a concept called microcode, which is that there was a little computer in there with a much more simple instruction set than the actual instruction set of the 8088 or 8086, 286, 386. And that little small micro engine interpreted the instructions that you gave it that were supposedly the machine language of the chip. And so it took several clock cycles of interpretation to handle every opcode that came down the line. The recent machines like the Pentium 3 are 1, and I believe the Pentium 4 is up to 1/2. It has gone down to less than 1 now. So, and we'll talk about how that actually does it in the Pentium 4. But if the combinational delays are too long, then pipelining may be the answer, because it'll cut down the amount of percolation that has to happen in between clock stages. If I ask myself the question, in this circuit over here, if I only have one register, and let's say that there was feedback from the output here back to these data values here, how often can I clock this without another register here? The answer is 1 every 1, 2, 3, 4 clock time units. Okay, because it takes 4 time units for the data to percolate down through the combinational logic that's here till I can clock this a second time. On the other hand, if I put another pipeline stage in here and hook the clock up to both of these, I can hit this clock how often? 1 every 2. Now I have to be careful because the data that's being fed back is a little bit delayed compared to the data that's being looked at and all kinds of stuff like that. And we're going to talk about just that issue in a few slides. But let's go back to the beta. Here is the beta that you remember, you know and love. It has, in its present form, only one stage. In other words, all this stuff up here is combinational logic. Numbers go in at the top, the PC, all this stuff, and then data just percolates down as fast as it can until it gets down to the bottom. And the data waits around at D and WD, WD, until this clock goes off, bang. And then once again, the new data values appear here, they percolate down until the clock goes off, bang. Okay. What could we do if we wanted to be able to hit that clock more often? Well, easy. Let's add pipeline stages. And in particular, we're going to look at what's called a 4-stage pipeline. And we're going to divide that vertical structure into the following 4 stages. One is going to be called the instruction fetch. One is going to be called reading the register file. The other one is going to be the ALU stage, which is where we actually do the calculations that are done. And then the last one's going to be called write back. And that's where we write the results back into the register file. And so here's the definition of these 4 stages. Let's take a look at what that looks like. The instructions will be fetched here. Then, once we know what the instruction is, we'll figure out which registers we need to read, and then we'll put a pipeline stage there. Then we'll do the operation in the ALU, a pipeline stage there, and finally we will write the results back to the register file. Looking at the diagram we had before, this single blue line that's down at the bottom, what we will add to that thing is 3 more blue lines at these stages over here. Now notice what I've done. I've hypothesized that the slowest unit in here is the ALU. And I have surrounded the ALU with registers. And then I've gone and I've kind of chunked the rest of the machine accordingly so that this is a stage, the ALU is a stage, this is a stage here where we read the register file, and this is another stage here where we look up, given the PC, what the opcode is that we want and feed it in here. And we should be able to clock this machine at a period which is equal to what? The maximum delay in any one of the stages. And all the clocks are going to go off at the same time. Kabang, everything shifts down by 1. Kabang, everything shifts down by 1. But any given instruction is going to take 1, 2, 3, 4 clock cycles to get done. And that's different than it used to be. It used to be that one instruction took 1 clock cycle to get done. Now, of course, those clock cycles are shorter than the 1 it used to take, right? It's not going to be quite a quarter, but it's going to be somewhat shorter. But hopefully, the overall clock speed of the machine should be faster. And every modern computer uses a technique like this with many clock stages.
They're not equal to zeros in RF.
Excuse me? Where is this? I think it doesn't matter because the result goes down so far. You could do it here, or you could do it here, or you could even do it here. I don't remember exactly where it goes. Okay, so here's 4 instructions, and the diagrams that we're going to use are going to be very similar to the one that I drew there before for the washer and dryer. So let's say that there was a sequence of instructions to add the constant 1 to R1, put the result in R2, subtract 1 from R1, put the result in R3, XOR R1 and R5, put the result in R1, multiply R1 and R2, and put the result in R0. And we're going to do these instructions one right after the other. Well, what's neat about this is that you'll notice that this instruction starts off and it fetches the add C. Next, it goes down the pipe by 1 stage, and each one of these lines here is a clock edge. And it starts to read the register file. And so it reads R1 right here. While it's reading R1, this instruction is being fetched from the memory, the big slow memory. And then when it's doing its ALU, this one is reading its version of R1 from the register file. And while that's going on, this third instruction is being fetched. Okay? And then as you see, going on and on and on, the instructions are being fetched along this line, RF is being read along this line, ALU along this line, written back along this line. And if there was another instruction coming along here, its instruction would be fetched right here. Yeah?
This means we can't do, we can't write back into a register that we're going to use in the next instruction as a source anymore.
These Harvard guys are smart. Amazing.
So does that,
Absolutely right. So
does
there
that mean
is
we change
trouble.
Our machine code specifications, or do we do something in hardware that will allow?
Well, we have to do one or the other. That's absolutely right. And so you'll notice that over here, there might be a problem. So let's talk about that a little bit. Let's consider this loop. Add R1 and R2, put in the results in R3, compare R3 to the constant 100, see if it's less than or equal to 100, and put the result of that into R0, branch if that's true to loop, XOR a bunch of stuff. What's the trouble in the diagram here? Well, just like you said, this instruction does not write R3 until the very, very end, until that end pipeline stage at the bottom of the beta. That's when it writes R3. But look at what happens here. Because we're willing to start this instruction, you see, in the unpipelined beta, we didn't start this instruction until after this one was done. But because it's an assembly line, we're going to start this one going before this one's done. And as a result, it's going to read R3 in its register file read stage before we write R3 over here. And so which R3 are we going to get? The R3 before this instruction went on, or the one that was after? The one before. So you scratch your head and you say, oh my God, this is terrible. Okay? And in general, systems with feedback like that have to deal with the fact that there's delay inside of the unit. Okay. EGADS. That must be what the EG stands for. Well, as you said, there are 2 ways to deal with this thing. The first is that you can program around it. You can tell the programmer of this machine, listen, when you write a register, it's not available for several clock cycles, and you better move any instruction that expects to get a new value to later on in the code. So I would move the compare less than from over here to later on down here, so that by the time I want R3, several clock cycles have passed, several other instructions have been sent down the pipe, and you can actually figure out from the machine how long you need to time delay it, so that instead of this line over here going from a write of R3, which occurs later in time from when we need it, we have the write of R3 happening just in time before we read it in this stage over here, if the compare is in this line as opposed to this one here. We read the register file here instead of back here in time. So that's one way to do it. The trouble with this is that when you build a processor chip, whether you're Intel or AMD or any of those guys, you generally build it according to what was called at the beginning of the semester an instruction set architecture. And the instruction set architecture has a semantic, which is basically saying these instructions act as if each one runs to completion before the next one starts. And if you now come out with a new chip that has more pipelining in it than the old one did, you can't then go tell all the people with code, hey guys, you got to rewrite all of your code because the new chip, even though it's faster, doesn't work anymore with the old code. The Pentium 4 still runs programs meant for the 8086 or the 8088, which was actually the first one. Okay, and the reason is that it doesn't do this. What's option 2? Well, the option 2 is whenever you get to a situation like this, you detect it. Okay, so inside of the computer is a dance card that looks like this, who gets to dance with whom when, and it basically keeps track of which registers are being written and when. And when it fetches an instruction like this compare less than or equal that wants a dance with a register that is destined to be read, to be written later, what it says is, well, you just got to wait, buddy. And it stalls the pipeline by inserting no ops or no operation into the pipeline. In this case, you need 2 of them, and sort of basically stalls the machine for 2 clock cycles and then allows the compare less than to go through. So it waits for the previous instruction to run all the way through. Now, what's good about this? Solves the problem. What's bad about it? It's slow, because you keep inserting these bubbles into the pipeline to wait for it to flush out before you let new things come through. And often, programmers often write code where they use the result of one operation in the very next one. And that means you're going to be doing this often. Okay?
Do compilers somehow optimize for this?
Absolutely. But that's kind of more like the previous thing, where what the compiler can do is say, you know I'm going to run on a Pentium 4, and even though maybe the Pentium 4 will do this, I know that that's true, so I can use the previous method and not trigger this to happen in real time.
So you could use the same C code that you used on the 8086,
Right.
but you'd have to use a different compiler to compile it to different machine code. Is that
Well, it allows a solution which is actually really a very, very nice one, which is, let's say the machine did this thing of taking a hiccup whenever it saw something bad. What it meant is that your computer could still run that old code, but it wouldn't run it fast. But if you recompiled it and the compiler was smart enough to try to move the compares to later on, then it would run faster. And so that's kind of a nice way to deal with the issue. But it turns out there's an even better way to do it. And it's realizing that even though if I write the result R3 over here and I try to fetch it over here, then I'm sort of messed up. The truth of the matter is, and this just happens to be true and it's nice, that I've computed what I'm going to write, not in this stage, but in this stage here. Here's where the ALU figured out what the sum of R1 plus R2 was, right at the end here, right on this edge. And here is where this ALU, independent of anything else, needed to know what R3 was. Now, R3 didn't get a chance to be stored, and we didn't get a chance to read it, but the data did exist in the machine somewhere, about to be written, after we had tried to read it, but we hadn't used it yet. And so maybe what we could do is we could short circuit a path in the machine and steal the data from here, clobber the answer that we got from here, and sneak it into the ALU before the ALU actually used the data. And believe it or not, this is done all the time. And this is called a bypass path, okay? And the idea here is that it's an extra data path and some quite sophisticated control logic in the machine. And what it's doing is it's sneaking a peek at what is about to be written to the register file, ignoring what was read from the register file here because it's old and stale, and substituting that data into the ALU rather than what it read. And we're going to see cases where the data does not yet exist in the machine and you have no choice but to stall.
How do you do this 1.5 billion times a second?
Well, that's a good question. That's an excellent question. It turns out it's actually not that hard, okay? In our machine, which I've put back up on the board here, what's wrong here? What's wrong here is that if you think about this cycle, we have register file, and how many registers are in the middle? 1, 2, 3, right? There's 3 registers in this feedback loop. And we used to only have 1 register. 1 register worked because that meant that there was 1 unit of delay between one instruction and the next one. So you could write a register, the clock could go off, and then the new value would come out here. But now we've inserted 2 more time delays in this loop. And as a result, it now takes 2 extra clock cycles before data gets ready. But we can just short circuit that by pulling the data off of here and putting it into this multiplexer. Let's say we're going to feed it into the left-hand side. We're also going to feed it into the right-hand side because we're not sure which side we're going to need it by. And that feedback loop only has 1 register in it. Just like our old feedback loop, before these 2 blue lines were here, down at the bottom only had 1 register in it. A feedback loop with 1 register works perfectly. It's a finite state machine. 1 clock cycle ends, bang, the clock goes off. The new clock cycle works depending on what happened in the last one. When we insert 2 more in the loop, we cause a problem with a time delay of 2. We short circuit it with this thing here, which gets us back to a time delay of only 1 clock cycle. And all we have left to do is to know when to tell the A selector or the B selector, if the data is going up here, when instead of choosing the register file, choose the bypass path. Why? Because the bypass path will have newer data compared to the register file. This value is old because it represents what was written 2 clock cycles ago. But if I click this one, instead of from the register file, I click it to this path here, I will get what was computed in the last clock cycle. And that's how we're going to solve the problem.
To do that, we need a way of comparing RC and the old instruction.
You betcha.
RA.
So we're going to take all this stuff and we're going to time delay it in different things. We're going to have a big, hairy piece of logic that's going to sit there and look at this dance card all the time and figure out how to move the multiplexers for the bypass paths, or if things get really jammed up, how to insert no ops into the machine, a bubble into the machine to slow things down. It'll be done in logic. No, it's actually going to be some and/or type logic. So, cool, huh? All right. That's the end of this lecture. What we're going to do next time is we're going to go into the gory detail of doing all this stuff, the bypass paths and the control logic. And guys, get this. Think about what happens. Let me just get you started on thinking about this. What happens when you do a branch? When you do a branch, the PC gets updated with a new opcode, right? The ALU output goes to here, and the PC, instead of choosing this, chooses that. Okay? So we get a new PC in here. How long does it take before the new PC gets back down here? 1, 2, 3, 4 more clock cycles, right? What happens during that time? Which opcodes are executed? The ones beyond the branch. Whoops, we told it to branch, but it's going to take 4 clock cycles to branch, so we keep, it's like a car that can't brake, right? You just keep on skidding for a little while. So we're going to talk about that, and we're going to talk about all the how to do this in the next lecture.